Fine, now we will discuss about the properties of oblique incidence of a plane electromagnetic wave at a plane dielectric boundary. That when you say plane dielectric boundary, which means that you have two media. First media is a plane, is a lossless dielectric media. So does second media. Both are lossless dielectric media. And first one having a parameters epsilon 1, mu 1 and eta 1, and second media having parameters epsilon 2, mu 2, eta 2, where epsilon is the permittivity, mu is the permeability and eta is the intrinsic impedance of the media. Now we again assume that the plane, the boundary, that is a plane boundary which separate the two media or which combines meets the two media, lies along the xy direction, or the plane is the xy plane, and the interface, naturally interface is at z equal to 0, and the normal lies along the z direction. So it's a very easy construction. You have a plane boundary which lies in the xy plane, and the boundary you keep it at z equal to 0. Normal to the boundary lies along z direction. Now you have an incident wave vector which travel along the direction a and I, and these are two rays in the incident plane wave, and it incidents at an angle theta I with respect to the normal. Okay, and naturally from O is the point at which one of the ray meets the interface. It gets reflected at an angle, say theta R, with respect to the normal. A and R is the direction of propagation, wave vector propagation of the reflected wavefront, and 3 and 4 are two rays in the reflected plane wave. And so again, if you drop a normal at this O dash is another point at which the incident ray throughout there is wave meets on this, and you just consider just two points O and O dash corresponding to two picked rays 1 and 2 of the incident. So it gets reflected as 3 and 4, and it gets transmitted into the second media as 5 and 6, and the direction of propagation is along A and T. The wave vector propagates along A and T at an angle theta T with respect to the normal to interface. Okay. Now if we consider, what I do is here I take at the point O. O is the point at which the ray 2 meets the interface, and from point O I drop a perpendicular to ray 1, and you have, when you say that the ray path is always perpendicular to the plane wavefront direction, you can see that we have plane waves incidenting, which means that OA actually shows the wavefront at this instant. Okay, OA is the wavefront of the incident wave. Similarly, I drop a perpendicular from O dash, that is from ray 4 at point O, that is at the interface is O dash. From this I drop a perpendicular to the reflected wave 3, which means that O dash A dash is the wavefront, that is the direction that is perpendicular to the ray path direction, or the wave propagation direction. That means it is again the wavefront of the reflected wave. Similarly, from ray 5 and 6 are the transmitted wave into the second medium. So we know that from O dash I drop a perpendicular to ray 5, which means that O dash, say this is B here, O dash B is the wavefront of the transmitted plane wave. So we have all the wavefronts here, and if you consider that the ray, ray 2 meeting at point O and ray 1 at A are happening at the same time. Okay, and by the time the ray 1 travel from A to O dash, the reflected ray travels from O to A dash. Okay, so O A dash nalla path first ray 2 reflect ചെയ്ത് ray 3 ആയിട്ട് O A dash എന്നുള്ള പാത്ത് ട്രാവൽ ചെയ്യുന്ന അതേ സമയം കൊണ്ടാണ് എന്ത് സംഭവിക്കുന്നത്, റേ 1 എ എന്നുള്ള പോയിന്റിൽ നിന്ന് O dash, അതായത് ഇൻ്റർഫേസിലേക്ക് മീറ്റ് ചെയ്യുന്നത്. വൈ? ബിക്കോസ് ഇത് പെർപെൻഡിക്കുലർ ഡ്രോപ്പ് ചെയ്യുമ്പോൾ ഇത് ഒരേ ഫേസിലാണ് ഇരിക്കുന്നത്. അപ്പോൾ ഒരേ ഫേസിലിരിക്കുന്ന രണ്ട് പോയിന്റ്സ് ആണ് ഒ ഡാഷും എ ഡാഷും. അതേപോലെ ഒരേ ഫേസിലിരിക്കുന്ന രണ്ട് പോയിന്റ്സ് ആണ് ഒയും എയും. ആൻഡ് വാട്ട് ഹാപ്പൻസ് ഇസ് ബോത്ത് ആർ ഇൻ ദ സെയിം മീഡിയ വിച്ച് ഇസ് ഹാവിംഗ് phase velocity equal to up1 in the first medium. So they travel the same distance by the same phase velocity, means the time taken will be same. Okay, so or the different, or conversely you can say that since the time taken by this ray to travel from A to O dash and the time taken for this ray to travel from O to A dash are same, and since they travel with the same phase velocity, you can say that the distance is also same. Time same ആണ്, velocity same ആണെങ്കിൽ travel the distance same ആയിരിക്കും. So you can say that OA dash is equal to AO dash. You can see that this angle, okay, the N at O, the angle between the incident and the normal is theta I. We know that. Okay, so if this is theta I, this angle, okay, the angle between normal and OA should be 90 minus theta I, because this is ray pathum OAയും perpendicular ആണ്. അപ്പോൾ ഇത് theta I ആണെങ്കിൽ ഈ ആംഗിൾ 90 minus theta I ആണ്. If this is 90 minus theta I, this part will be theta I. Okay, so A O O dash, angle A O dash is theta I. So in the right angled triangle OAO dash, what we know is angle O is theta I. If angle O is theta I, A is 90 degree, so OO dash is the hypotenuse, then AO dash you can write as this is theta I, then AO dash is the opposite. Opposite by hypotenuse is sine theta I, so opposite is equal to sine theta I into OO dash. So AO dash is equal to OO dash sine theta I. So you got this AO dash in terms of sine theta I. Now if you consider the other one, that is you have perpendicular from O dash to A dash. Okay, this is your perpendicular. So what we know is this angle, normal and the ray path OA dash is theta R. So this angle is angle A dash O dash is 90 minus theta R. If this is 90 minus theta R, you can say that this angle O dash is theta R. Okay, because this is 90 degree. So in the right angle triangle OA dash O dash, this is angle O dash is theta R, which means that A dash O by O dash O is sine theta R. So A dash O is O dash O sine theta R. So you can equate from the equality OA dash equal to AO dash. What you get is OO dash sine theta R equal to O dash sine theta I. OO dash random same ആയതുകൊണ്ട് you can get as sine theta R equal to sine theta I, or you can get it as theta R equal to theta I. The angle of reflection is equal to angle of incidence. So this is Snell's law of reflection irrespective of the polarization. Okay, now if you consider about the transmitted, what we know is this is the wavefront, O dash B is the wavefront, and by the time the ray, an incident wavefront OA reaches O dash, okay, ഇവിടെ നിന്ന് ഇവിടെ എത്തുന്ന സമയം കൊണ്ടാണ് O എന്ന് B എന്നുള്ള ഡിസ്റ്റൻസ് ട്രാവൽ ചെയ്യുന്നത്. ഓക്കെ, സോ ദാറ്റ്സ് വൈ യു ഹാവ് എ പെർപെൻഡിക്കുലർ ഫ്രം ഹിയർ, ഇവിടം വരെ സെയിം ആണ്. എന്ന് O ഡാഷ് എത്തുന്ന സമയം കൊണ്ട് ഓയിലെത്തുന്ന light or electromagnetic wave travel by a distance OB. So the time taken for the light or the electromagnetic wave to travel a distance AO dash in the region 1 with the phase velocity up1 is equal to the time taken by the wavefront which reach at O to travel a distance OB in the second media with say phase velocity up2. So the time is being saved. So you can say that the distance AO dash by phase velocity in the region 1 is equal to the displace or the travel distance OB by UP2. The time ആണ് നമ്മൾ equate ചെയ്യുന്നത്. So OB by UP2 is equal to AO dash by UP1. So OB, again from this right triangle, you can say that this is theta t, which means that this is 90 minus theta t, and angle O dash is in O dash B. This is theta t. So OB by O dash is sine theta t, or OB is O dash sine theta t. So OB by AO dash is O dash sine theta I. That is, we know it from here. It is equal to UP2 by UP1, and from this what you get is sine theta t by sine theta I is equal to UP2 by UP1. Now we know UP2 is omega by beta 2, UP1 is omega by beta 1. So what you get is sine theta t by sine theta I is beta 1 by beta 2. And we know if you take their non-magnetic, you can write U1 is approximately equal to mu 0, and mu 2 is also approximately equal to mu 0. So you can write it as beta 1 by beta 2, you can write as root of epsilon 1 by root of epsilon 2. So epsilon 1 is, root epsilon is refractive index. So root epsilon 1 by root epsilon 2 is n1 by n2. And we know that eta is root of mu by epsilon. So this can be, since mu are equal, assumed equal, can be written as eta 2 by eta 1. So what we got is the ratio of sine of angle, sine of transmitted angle to sine of incident angle is actually the ratio of, inverse ratio of refractive indices n1 by n2, and it's equal to root of epsilon 1 by epsilon 2. Now you take the case with epsilon 1 greater than epsilon 2. What does it mean? The region, the incident medium is denser than the reflected medium. So we are going to consider the case where the first medium is of higher refractive index, or higher denser than compared to the second medium. Okay. In that case, we know that epsilon 1 greater than, the ratio will be greater than 1, which means that sine theta t will be greater than sine theta I, which means that sine theta t will be greater than theta I. Also, we know that the ratio is constant, which means that if you increase theta I, naturally theta t also will increase. Now you go and increase theta I such that theta t becomes 90 degree. Okay, when theta t becomes 90 degree, what you get is sine 90 degree by sine theta I equal to root of epsilon 1 by epsilon 2. So this is a constant one, and theta t becomes exactly 90 degree, which means that you have a perfect single value for sine theta I for which this equality holds. So that particular angle at which transmitted angle becomes 90 degree. When transmitted angle is 90 degree, which means that it lies along the interface, the boundary. That particular angle is known as your critical angle, and that critical angle, if you put it here, you will get it as sine theta c equal to root of epsilon 2 by epsilon 1. Okay, and when theta I is greater than this theta c, we can see that theta t becomes greater than 90 degree, or which means that it comes back to your medium 1, and what we call as total internal reflection, that is known to us. Okay, so this critical angle at which the transmitted direction is racing through the boundary is called as the critical angle, above which if the incident angle increases, it happens that the transmitted ray comes back to this first medium, and we call that you have total internal reflection. So rewriting it, you will get it as sine theta t can be written as root of epsilon 1 by epsilon 2 into sine theta I. This is actually the basic Snell's law. Now when you have sine theta I is greater than theta c, that is the case with transmitted wave, the total internal reflection, you can say directly, you can write sin theta I is always greater than sin theta C. And we know that sin theta C is epsilon root of epsilon 2 by epsilon 1, that is a fixed value. So when this happens, when theta I is greater than theta C, sin theta t, what happens to sin theta t? Now why it is important, we'll come to that. Okay. Sin theta t you can write as root of epsilon 1 by epsilon 2 into sin theta I, which will be greater than 1. Definitely. Why? Because sin theta t, when theta I equal to theta c, it is 1. So for any theta I greater than theta c, you can see that sin theta t will be greater than 1. So how it is possible? It is possible because sin theta can be greater than 1 in complex plane. Okay, now we'll come to that. If sin theta t at theta I equal to theta c, you write it as sin theta tc. You can write this is equal to root of epsilon 1 by epsilon 2 into sin theta c, and this is equal to 1 where theta tc is pi by 2. Okay, this is known to us. Okay, so what happens? How can you represent cos theta? You know that cos theta is root of 1 minus sin square theta. So you write it here, cos theta t equal to root of 1 minus sin square theta t. Now, if theta t is, sin square theta t is greater than 1, what happens? Root of 1 minus sin square theta t. Okay, cos theta t എന്ന് പറയുന്നത് purely imaginary ആണ്. So you can write this is equal to plus or minus j into root of sin square theta t minus 1. ഇത് തീറ്റ ഐ എന്ന് പറയുന്നത് ഇൻസിഡന്റ് ആംഗിൾ ക്രിട്ടിക്കൽ ആംഗിളിനേക്കാൾ ഗ്രേറ്റർ ആവുന്ന കേസിലാണ് നമ്മളിത് എടുക്കുന്നത്. ഓക്കെ, തീറ്റ ഐ ഗ്രേറ്റർ ദാൻ തീറ്റ സി ആവുമ്പോൾ നമ്മൾ ഈ ഇക്വേഷനിൽ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുകയാണെങ്കിൽ സൈൻ തീറ്റ ടി എന്ന് പറയുന്നത് എപ്സിലോൺ 1 റൂട്ട് ഓഫ് എപ്സിലോൺ 1 ബൈ എപ്സിലോൺ 2 ഇൻറ്റു സൈൻ തീറ്റ ഐ എന്ന് വരും. നമുക്കറിയാം സൈൻ തീറ്റ ഈ വാല്യൂ ഫിക്സഡ് ആണ്. സൈൻ തീറ്റ ഐ എന്ന് പറയുന്നത് സൈൻ തീറ്റ സിനേക്കാൾ ഗ്രേറ്റർ ആണ്. ഓക്കെ, എപ്സിലോൺ 1 ബൈ എപ്സിലോൺ 2 ഇൻറ്റു സൈൻ തീറ്റ സി 1 ആയിരുന്നു. അപ്പോൾ എപ്സിലോൺ 1 ബൈ റൂട്ട് ഓഫ് എപ്സിലോൺ 1 ബൈ എപ്സിലോൺ 2 ഇൻറ്റു ഒരു ക്വാണ്ടിറ്റി എന്ന് പറയുന്നത് എന്തായാലും 1നേക്കാൾ ഗ്രേറ്റർ ആയിരിക്കും. അപ്പോൾ അതിന് കാരണം കോംപ്ലക്സ് പ്ലെയിനിൽ. അപ്പോൾ അതെങ്ങനെയാണ് നമ്മൾ നോക്കണമെന്ന് വെച്ച് കഴിഞ്ഞാൽ നമുക്ക് സൈൻ തീറ്റയ്ക്ക് എന്തായാലും ഒരു റിയൽ വാല്യൂ ഉണ്ട്. പക്ഷേ സൈൻ തീറ്റ ടി വെൻ തീറ്റ ടി സി എന്ന് പറയുന്നത് 1 ആണ്. പക്ഷെ തീറ്റ ടി ഗ്രേറ്റർ ദാൻ തീറ്റ ടി സി ആകുമ്പോൾ ഇങ്ങോട്ട് ഇപ്പുറത്തേക്ക് വരികയാണല്ലോ ചെയ്യണം. ഇതിനേക്കാൾ വന്ന് ഗ്രേറ്റർ ആവുകയാണ് ചെയ്യുന്നത്. അപ്പോൾ അതിന് നാച്ചുറലി സൈൻ തീറ്റയ്ക്ക് നമുക്കൊരു റിയൽ വാല്യൂ ഉണ്ടാവുന്നുണ്ട്. ബട്ട് വാട്ട് ഹാപ്പൻസ് ടു കോസ് തീറ്റ ടി ഇസ് കോസ് തീറ്റ ടി ബിക്കംസ് ഇമാജിനറി. ഓക്കെ, അപ്പോൾ കോസ് തീറ്റ ടി ഇമാജിനറി ആയതുകൊണ്ട് നമ്മുടെ വേവിന് എന്തെങ്കിലും പ്രശ്നമുണ്ടോ? ദാറ്റ്സ് വാട്ട് വി ആർ ഗോയിങ് ടു തിങ്ക്. നമുക്ക് സൈൻ തീറ്റ ടി സി എന്ന് പറയുന്നത് 1 ആണ്. സൈൻ തീറ്റ ടി സി എന്നതിൻ്റെ തീറ്റ ടിനേക്കാളും ഗ്രേറ്റർ ആയിട്ട് വന്നു കഴിഞ്ഞാൽ ടി സിനേക്കാൾ ഗ്രേറ്റർ ആയിട്ട് തീറ്റ ടി വരികയാണ്. എപ്പോൾ തീറ്റ ഐ എന്ന് പറയുന്നത് ക്രിട്ടിക്കൽ ആംഗിളിനേക്കാൾ ഗ്രേറ്റർ ആകുമ്പോൾ. അങ്ങനെ വരുമ്പോൾ നമ്മൾ കോസ് തീറ്റ ടി പ്യുവറായിട്ട് ഇമാജിനറി ആകും. വാട്ട് ഡസ് ഇറ്റ് മീൻ? അല്ലെങ്കിൽ അതുകൊണ്ട് എന്താണ് വേവ്? അപ്പോൾ നമുക്കറിയാം ഇതാണ് എ എൻ ടി ഇസ് ദ ഡയറക്ഷൻ ഓഫ് പ്രൊപ്പഗേഷൻ ഓഫ് യുവർ വേവ്. ഓക്കെ, അപ്പോൾ ട്രാൻസ്മിറ്റഡ് വേവിൻ്റെ ആംഗിൾ തീറ്റ ടി ആണ്. അപ്പോൾ എ എൻ ടി ആണെങ്കിൽ അതിനെ നമ്മൾ സോൾവ് ചെയ്ത് എഴുതുമ്പോൾ യു ക്യാൻ റൈറ്റ് ഇറ്റ് ആസ് എ സെഡ് കോസ് തീറ്റ ടി പ്ലസ് എ എക്സ് സൈൻ തീറ്റ ടി. എ എൻ ടി ഇതാണ്, ഇത് എക്സ് ഡയറക്ഷൻ ആൻഡ് ദിസ് ഇസ് യുവർ സെഡ് ഡയറക്ഷൻ, ദിസ് ഇസ് ആംഗിൾ തീറ്റ ടി. So you can resolve them into x and z components as a z cos theta t plus ax sin theta t. So every term et of z ആണെങ്കിൽ zx ആണെങ്കിലും ht of zx ആണെങ്കിലും you have a phase term equal to e raised to minus j beta into ant dot r. So beta എന്ന് പറഞ്ഞാൽ beta 2 ആണ്. e raised to minus j beta 2 into ant dot r is here it comes as z cos theta t plus x sin theta t. So there is a term which includes cos theta t in your transmitted wave. Okay, so sin theta t we know that it is equal to root of epsilon 1 by epsilon 2 into sin theta I. quiet domain. But cos theta t is plus or minus j root epsilon 1 by epsilon 2 into sine square theta I minus 1. This is below. But what we do is you take only the minus j value, the plus j value if you add, you will see, you come to see what happens. So substitute this cos theta t and sin theta t in the phase term, you get e raised to minus j beta 2 into minus j root of epsilon 1 by epsilon 2 sin square theta I minus 1 into z into x term e raised to minus j beta 2 into sin theta t is root of epsilon 1 by epsilon 2 into sin theta I into x. So you can write, it can be written as e raised to minus j beta 2x into x into e raised to minus j into minus j. It goes like, it cancels and become a real value. So you can write it is, apparently it looks like e raised to minus alpha z into e raised to minus j beta 2x into x. Maybe alpha 2, where alpha 2 is the attenuation in the second medium, which is equal to beta 2 into root of epsilon 1 by epsilon 2 into sin square theta I minus 1, and beta 2x you can write as beta 2 into root of epsilon 1 by epsilon 2 into sin theta I. So it depends on the value of epsilon beta as well as on the value of theta I. What does it mean? You can see that it corresponds to attenuating wave which travels along the x direction. So if this is your interface, you can see that you have a wave propagating along the x direction, even though that is in the second media, and it exponentially decreases as alpha e raised to minus alpha z. But as you move away from the boundary, ഇത് exponentially in the amplitude കുറഞ്ഞു വരുന്നു. പക്ഷേ it travels along the x direction, along the interface. How? Because we have taken it as either case with theta I greater than theta c. So by ray optics, what we know is for theta I greater than theta c, it occurs into total internal reflection. Total, when we say total internal reflection, there is no wave is transmitted to the second medium. That is what we have learned. But you can see that you have a surface wave in the second media, but which is traveling along the x direction. Interface in the direction that traveling with the wave under, but it is not perfectly zero to the other side. You have a surface wave which decreases its amplitude exponentially with z. So there is only a small region in the second media where you can see this wave, and its amplitude is higher at the surface, and it slowly, or not slowly, it exponentially, drastically decreases to with z value, perpendicular direction. And such waves which are transmitted along the interface, the surface wave, are known as evanescent wave. Okay. It's evanescent wave which is being transmitted along the boundary, and they are surface waves. Okay. So all these things happens irrespective of the polarization of the wave. But what the ratio, the transmitted intensity, reflected intensity, all depends on the polarization and the polarization of the wave. Here, we transmit the total internal reflection, whatever be the Snell's law, the reflected angle, all independent of polarization.